Okay, so we are going to see inner product spaces. Okay, so what is inner product spaces? Throughout throughout this lecture, throughout this lecture, K is equal to R or C. Okay, it means K is a field or K is either real field or complex field. Okay, so what is inner product space? Inner product space. Okay, so let X be a vector space over K. Okay, an inner product on X is a function. Function is denoted by this way. Okay, from X cross X to from X cross X to K such that for all X, Y, and Z, for all X, Y, Z in X, and K belongs to capital K in, okay, we have, what we have this one. Number one, positive definiteness. Positive definiteness, this property is called positive definiteness. Let's say that X is always non-negative. Okay, if you take same thing in both the slots, it will be non-negative. And X is 0 if and only if X is equal to 0. Okay, X is equal to 0. Second property is linearity in first variable. Linearity in first variable. What does it mean? It means you fix second variable and varies first variable, then it will be a linear functional. So this is plus yz. Okay, and kxy is equal to k times xy. Okay. Third property is uh, third property is conjugate symmetry. Conjugate symmetry means what? Yx is actually nothing but conjugate of xy. Okay, conjugate of xy. Note that this is inner product is conjugate linear in second variable. Conjugate linear in second variable. Okay. Conjugate linear in second variable. Okay, how? Conjugate linear in second variable, because you see that if I fix x, y plus z, so from here, what we have actually, we can also write x. This happens if and only you taking both the side bar. What can you say? This. Okay. So what is this actually? This is nothing but y plus z x ka bar. In first slot, it is linear. So inside thing will be like this. So since conjugation is distributed like this, so we can write. So what is this? This is nothing but xy. Okay. And what is this? And ky x k times y. What is this? I can write this ky x ka conjugate. What is this? So so it will be inside thing will be this. So what is this? K bar. Okay. So it means, so these two properties, that means that this function is conjugate linear in second variable. Conjugate linear in second variable. Okay. Okay. Note an inner product space is a linear space. Linear space is also called vector space. Okay. वेक्टर स्पेस का दूसरा नाम लीनियर स्पेस भी होता है. So an inner product space is a linear space with an inner product on it. Okay. 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 So properties. So I am writing lemma. So some examples. So I am taking L2N. L2N is nothing but sequence. Okay. K such that n goes 1 to infinity. Okay. So we define let x, y, So let x is equal to alpha n and y is equal to beta n. Two sequence I'm taking from L to n. Then I am defining the inner product in this way. Okay, in this way. My claim is that L to n with this inner product this is an inner product space. Okay, so actually you can check all the properties. It will be inner product. To checking inner product, first of all, your this kind of thing should be well defined. So how you know that this will converge? Because this is a series. Absolutely summable series is summable. Okay. And you also know that if something is a L1, if something is a L1N, then L1N actually properly contain in L2N. So if I can show that this series n goes to 1 to infinity, alpha and beta and bar is that means one summable I'm going to prove. By Holder's inequality, we have this one. By Holder's inequality, we have this thing. We know that if alpha n sequence is in L2, its bar sequence will be also there. So what is this actually? Summation n goes to 1 to infinity, alpha n square 1 by 2 summation n goes to 1 to infinity, beta n bar. This will be this. Each part is finite. Each part is finite. So this part is that means alpha and beta and bar. This sequence belongs to L1 and that means this is well defined. Because if series absolutely convergent, then it is convergent. So rest the properties can be checked easily. The properties can be checked easily. Okay, so L to N is an inner product space. Okay, actually, actually, we can also define L to Z also. How? We can define like that alpha n belongs to Z such that summation n goes to minus infinity to infinity an is less than this way we can define. Okay, okay, or you can write like that because writing n infinity is not good like so you can write minus or you simply write n belongs to Z. That will also work. Okay. Similarly, suppose if x is like this, alpha n belongs to Z, and y is actually this, n belongs to Z, and these two belongs to L to Z. So I can define an inner product in this way, n belongs to Z. Okay. You can check that L to Z with this is an inner product space. Okay. Example 2. Example 2. What is C double note N? C double note N is this is sequence in Kn such that there exists capital N belongs to natural number such that alpha n is 0 for all n greater than equal to capital N. It means after certain stage all the terms become 0. So let x is equal to alpha n and y is equal to beta n. These two x and y are belonging to C double naught n. Then I can define same inner product in a same way alpha n beta n का बार ठीक है okay so check that C double naught and this is an inner product space okay is an inner product space okay example 3 example 3 um, so CAB CAB I want to continuous function on closed interval AB. So f and g I am taking. A and B are finite. Okay. So I want to define an inner product on this. What is the way? A to B. A to B, FT, GT का bar DT. Okay. Okay. You can check that CAB with this is an inner product space. More generally, more generally, we can define inner product on L2. CAB actually contain in L2AB properly. Okay. So we want to define more generally. So let F and G belongs to L2AB. So I can similarly define inner product A to B FT D GT का bar DT. Okay. Okay. Similarly, 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 check that this is an inner product space. Okay. Okay, so many examples will be there. Okay, so